My name is Vasyl, and I'm from Big Bear Soil Observatory, which is about 3-hour drive from here toward the east in the mountains. And we have a 1.6 meter telescope that we operate now for about 10 years. So today I'm supposed to share experience, but what I will show you a lot of bad data. And essentially it's for you. You've seen nice images already, but what I thought I will show you what you can expect in real life data and how to recognize things that are not there. We already heard a lot about adaptive optics, and I'm not going to talk about it. I just want to show that this little mirror, where is it? Over here. This is the formal mirror that will actually determine how much trouble you will get with your data. It will provide you very good data, but also at times it will create a lot of troubles that you will have when trying to prepare data. Because speckle reconstruction itself is very easy in a way. In a way, you create those data files that you just try to do, and you write script, and it works for you overnight. In the KISS case, it will work in real time. However, I suspect that sometimes you will have a possibility to observe and get bursts of data. So you will try to reconstruct them yourself. So this is the formal mirror that we'll try to create and provide you with nice images. So effect of AO. So here you have a granulation field was speckle reconstructed, but AO was not working. So yes, we do and can recognize granulations all over the place. However, this image in this way, not really useful because you cannot do much science here. So next image, I'm not sure how good the projector is. This is raw image corrected with AO. And you can see that, for example, that raw image is way better than only speckle reconstructed without adaptive optics. And here you have AO and speckle image. Those are the same. So you can appreciate the difference. You can see a lot of, well, at least bright points here and intergranular lanes and more structures. So another image, raw image without AO, as you would see is on the screen when you take data. This is not particularly good image, neither is bad image. It's just sometimes average image. And you can see, again, granulations and maybe sometimes spot bright points. However, again, if you run speckle code on that image, it will not produce good results. However, when you turn on adaptive optics, the image gets a little bit better. And you can see already bright points, which basically those bright points are concentrations or places where you have very strong magnetic field. And sometimes interesting to understand the dynamics, how they move, how they change, how they evolve, because it determines, in many cases, well, let's say, energy release on the sun. Again, when we do speckle reconstruction, it gets a little bit sharper. And here, you can appreciate the difference between those two images, only AO and AO plus speckle. The bright points are very sharp. Now you can do some automatic detection or tracking of those elements, or whatever you want to study. So speckle reconstruction. This is the same GUI, but a little bit different shape. But you can recognize now those parameters. When we started to observe back in 2009, we didn't have a lot of computational capabilities. So one of the problems was that we wanted to reduce the runtime and disk space. So we started from taking 100 image bursts and then speckle reconstructed. And we found that it takes a lot of time. So we were thinking about what we can do. And we did a lot of experimenting. For example, take the same burst and reduce number of images in the burst. And also play with those parameters. And we found that, for example, a combination of 6, 60, 5 iterations, and 90 this percentage works well in case you have very good seeing conditions. So that reduced a lot of, for us, computational time, especially almost twice, without really making any visible or significant difference in the output. Another thing, what we did, we do image selection. So when we observe, we take 100 frames, and then we save only 70 best frames as determined using contrast, image contrast. So what we can gain here, we can reduce the cadence. For us, it was important because you spend less time on saving data, and also shorten processing times and storage and everything like that. So in case of, for example, when we observe photosphere, we found that we can throw away 30 worst images and still get result which is quite acceptable. When you have really good seeing, you can drop about 50 images and still have good data.
Those results, are they specific to the Speckle code that you guys are using, or would you say?
I think it's specific to the Speckle code that we use, and we use the same Speckle code that you do here.
Good.
So they are specific. Apparently, I think another Speckle code would produce different results because it's based on different techniques. Some maybe codes, not necessarily Speckle codes, image restoration codes, would require different size of bursts. Some of them may not require bursts at all. So there is different approaches, but this one requires to take data in bursts. I don't know if it was very specifically discussed. So what happens was we run a camera at about, let's say, 40 frames per second cadence. So you collect 100 bursts. You do what you want, and you save that burst. In our case, because we don't do real-time reconstruction. So, and then after that, we do reconstruction. So from each burst, you get one image. So the only question is, how big is the burst? What we did, I have done this many, many years ago. I just found those plots. For example, this is an error of reconstruction. And that's how many images we use to reconstruct. So this is 100 images, 90, 80, or I believe 70, 60. So when you reduce the number of images or the size of the burst, your accuracy decreases. However, same here. However, what we do image selection. So you take 100 images, and we select, let's say, 90 best, or 70, or 60. And do Speckle reconstruction. And as you see here, the error does not really, well, it does, but to a certain degree, does not depend on the image size. In fact, what happened was, when we removed the worst 30 images, the final image, the quality of final image has increased. Because apparently if you have very bad images, they really do not add to the image reconstruction, they actually take away. However, if you go over 70, let's say 60, 50 or less, then it creates a problem. So now, on several decayist workshops that I attended in general, people have this attitude or desire, wishful thinking that you take decayist or GST or any other ground-based telescope You point at the sun, and you will be getting 6 hours of images like Hinodel type or SDO. Everything nice and stable, no problem, stable scene. And sometimes we wish, oh, every time we observe, data would be that good, stable. I did not align those images. It just, as they were coming from the telescope, I made this quick line view movie. However, the reality is quite different. You will not get this kind of data all the time. I'm not sure how the KISS will perform, but good data will be coming not every day. So for example, this is one burst, not corrected, not even flat fielded. So you see that this data is pretty good, relatively stable. AO is working well. And if you do Speckle reconstruction, you're getting pretty good results. This is another example. You've been talking about ugly. This is January 2nd, after store, after New Year. Maybe some kind of hangover there too. But anyway, as you can see, the data was very good, very bad. Because again, a lot of image quality depends not only how AO performs, but also on the weather. And for example, in particular in Big Bear, when we have Santa Ana winds, which is basically wind coming from northeast from the desert, which is usually dry and cold or hot. But either way, we never get good seeing. And for example, in our case too, if there is no wind, the seeing is never good either. So when we start to observe, we usually look in the windows in causeway, and there are bushes. And if bushes don't move, we don't expect anything good. Sometimes it might happen, but normally we look at the wind. When the bush start to move, you can see in the monitor things getting better. So but this is particular only about our side because we have lake, we have mountains. It's pretty high in the mountains. So in Hawaii, the case could be different case, but still it very much will depend on the weather. So this is bad seeing, and this is what you get. Well, you have a sunspot, you have a light bridge and a pore, but that's about it. Nothing else is there. Another example, again, granulation is pretty good. One of the facts that happens, and I think Kevin was showing today, that very often when seeing is getting bad, this isoplanatic patch becomes smaller and very well pronounced. So what you have is looks like what we call like tunnel vision. You have very sharp center over here, and then starting from there radially is basically it's out of focus. The further you get away, the less focus it is. So when you do spectral reconstruction of such an image, you will see that this center is really, well, over-reconstructed. Those features too bright, granulation is too bright, and bright points are too bright. It's not only they are too bright comparing to that area, but also in general. If you compare it to normal, well-reconstructed photosphere, this center is too bright. So if you see an image that has this excessive brightness in the middle, it tells you that your AO system was struggling reconstructing only the central part, and you still can use it if you follow evolution or something, but if you want to make any conclusions about, for example, brightness variations, probably not, better not to do it. Another case when you have bad seeing, but without this bright patch in the middle, you can see that sharpness is not good all over the image. There's another type of behavior of adaptive optics. It all depends on what kind of turbulence you have. Because today Sam mentioned about MCAO. It's basically a system that corrects on 3 different levels. So it depends which level would be dominating. You may have different results, but still this is kind of data you can get, and you can easily spot problems there. Another example, a pore. So that one image was okay, and then a certain period of time, you start to have problems. You have all these very bright, actually edges of granules and features inside a pore. So again, that's the signal for you that you have to be careful about with that image. Very often, people ask or complain, including referees, that how you know that things that you see in the images is real, not some kind of artifact of image or speckle reconstruction. And very often we have to go back and look at the raw image and see if that particular bright feature or dark feature is there, and you find it and you say, well, here it is. It's not as sharp, it's not as good, but it's real. It's not something that Speckle creates. Because since Kevin mentioned today about black magic, so many people have this idea that this is black magic, and it just makes up things in the image, so you cannot really trust it. Essentially, I had a referee once saying things like that. So Speckle code does not create things out of nothing, or because I just want it and just randomly put your bright point over here in the middle of granule into granule lane. It does create artificial things, but it's easy to spot them in a way, and that's basically.
Yeah, I was just going to ask if on the right this is a reconstructed image, and if so, are the bright features in the pore
These ones?
artificial? Yeah.
The intensity is not correct, overestimated, but they are there. And if you look at the raw image, you will see them. They are not artificial.
Can you run the reverse procedure and show that? Because it looks like if you smear those bright features, it would not match the image on the left. It would be much.
It might be. The reason thing is there is 1 hour and 1.5 hour difference between those images. But again, it does not just out of nothing creates randomly stuff. What it does is something like that. For example, this is observation very close to the limb projection effect. And for example, it happens over here that there is no features because this is chromosphere, you don't have jets. The granulation in this case, for example, in chromosphere, granulation has very low contrast. And because of projection effect, basically, you don't see here anything. So it's hard, for example, for AO to work and properly to work. And also, it's hard for Speckle code to reconstruct those areas where essentially there is no contrast. So as a result, you may see that when seeing is very, very good, it still looks okay and you can pick up some features, but very often everything is smeared and nothing is there. Instead, what you see, some kind of strange lines inclined and then I think vertical. So when you do these observations or you plan observations, especially if you're interested in the chromosphere, and you probably would be possible even to reconstruct some chromospheric images from DKIST. You have to make sure or understand that this kind of observations or areas where it's low, very low contrast, it might be large filament, it might be disk-wide sun area, or maybe even large sunspot. Speckle reconstruction may fail in those areas and may not work properly. Speckle code also enhances a lot of features that you may not see in the image. For example, those are fringes from because we observe this interference filter with very narrow band filter. So you can create fringes on the entrance window of the camera. So in order not to get that, you have to tilt a little bit camera to the side, so to remove the fringes. But sometimes it happens they are here. And when you observe, see a live image, you will not see it. But when you do spectral reconstruction, you see all those fringes. As I said, I'm showing bad examples just for you to get somehow feeling what you can see in the data. It doesn't mean that we observe like that every day. I think a lot of people in Big Bear would be upset that I'm showing bad data. Another example, this vertical line. I don't think it's a very good example. Here, it's way better. We had a problem with the camera at some point because theoretically you can take flat field images. You don't have to take flat film images at the same exposure that you take data. However, this particular camera has problems, so it was creating one bad row. And the position of that row depended on the exposure. So when you take data and then flat field using images with different exposure, that row would not correspond to each other and would introduce all kind of different mess. However, this is not the problem. The problem is that that bad row is very well visible. And I don't know if you see it well, but what happens is along that line you see very faint and narrow parallel lines. It's almost like a kind of diffraction pattern. And I tried to find an image when we had bad pixels and actually dust. I remember we had one when we did speckle reconstruction without flat fielding. So you would have in those images, bad pixel, and then almost constant rings around it, several rings, because this is how speckle performs. This is what artifacts it creates. So I'm showing this for you to see that, understand that any of those bad things, they can be immediately recognized. Dust. So you see here, and there dust. So you can see them, and you can say that this is not real feature because it creates, usually when you have very bright points, very often speckle would create a dark ring around it or other way around. So that's what you can see, bright and dark features around it. So you have to be careful, especially when you look at very small features. You have to be careful, but you do not have to be afraid that each feature here is some kind of artificial or not really, really there. And I guess last image would be, this is an example of a filament. Because the filament was dark, essentially nothing here, there is no contrast, no feature, speckle sometimes fails. And what you see here, there's a little square. It's this subaperture where speckle uses to reconstruct. But what happens is, maybe a new version doesn't happen. Sometimes it takes this one subaperture and puts it in the wrong place. So you can see here, and I think another sign over here. Very often we can see that in large sunspots. When you have a very large sunspot and has strong magnetic fields, it's very dark. It doesn't have a lot of umbral dots. It means that there is no really features for speckle to reconstruct or to co-align. And what happens is you will see those little boxes inside the sunspot. Again, I've been told that it's possible to correct and move them back where they belong, but we haven't done this yet. I guess I will finish here. And I just want to tell you that this technique is very exciting. It is indeed magic when you feed the data into that, I don't want to say black box, but pretty much. And you're getting out really nice images. And for you, I don't know how the KISS will operate, because some data would be reconstructed not online, real time, so you will not have a chance or possibility even to go back and do your own speckle reconstruction. Maybe you can have that chance if you have some kind of connection with the KISS people. They will offer you. I'm not sure. Are you going to save this raw data? No. Yeah, because it's a huge amount of data. But for example, when you plan to observe using other instruments, you may try, for example, to run and get bursts of data. When we do speckle reconstruction of H-alpha, we actually use 25 images. We did again testing, and we found that difference between 70 and 25 is really, really, really small. And because we need to a lot of this space, because we save and keep all the old data, raw data, yes. So if somebody wants to do their own speckle reconstruction, we can extract all the bursts and give you to play or reconstruct or whatever. So we keep the data. So we do 25. And even it's possible to do even with 10. It will not be as good as 100, but if you have choice, one image or reconstructed using 10 images, that would be, in my opinion, much better and will give you higher quality. However, it depends what you want to do, because the longer burst is, it means you lower the cadence. So that's one of the compromise you have to do. You either go for spatial resolution or for cadence. People are greedy in general. They want both, and it's not always works. So depending on your task, what you want to do, you want to study very short-lived jets or type 2 specules or RBEs or something else. That means you want to have as many images as possible in order to track those features. But if you're looking for something more long-living events, you might do lower cadence and do speckle. So I guess that's kind of our experience. The code works well, and depends on what kind of data you get and how telescope performs. Thank you. Questions? No.
So you showed us the parameters for good seeing. What if you have mediocre seeing? What parameter do you adjust?
We don't adjust. No, because if you have mediocre seeing, you adjust, you will not get better. Maybe yes, but if you have during our observation in summertime, we don't get as much as the KIST, but we do have thousands of images, and there's no way we can analyze and say, oh, this first hour we use this and second hour that. And besides, it will not make a difference. At least it's too time consuming. Again, since we have raw data, everybody is invited and welcome to get this raw data and have fun, but but we don't do that.
Yeah, so you mentioned that you take a longer series of images, like 70, and you choose the 50 best images according to some length. But doesn't affect the statistic in Speckle from estimating what happens in a way that you use the images to estimate what are zero.
Yeah.
In a statistical way, but if you're biasing the prior.
Yes, it does. So that's why when I said 50, this might be working only when you have really good seeing. When you essentially look at the real-time data on the monitor and you don't see as a phonetic patch. So when you really have a good seeing, you can reduce that. Only that makes sense if you your ears. Only if you want to get high cadence. For example, in our case, this, the KISS case probably doesn't matter but in our cadence, you can do that. However, but normally we observe at 70. We take 100 and then we take 70 best. Because when you reduce lower than that, the image quality drops. So it's all about what you want to do, but it's possible.
Any more questions? I have a comment before everybody is so scared that they go and do apply cosmology on the light. Right. That one of the important part of doing solar physics from the ground is that not all your data sets are of consistent quality, right? I mean, you might be used to more or less a space instrument has instrumental problems and drifts and whatnot, but the image quality is consistent.
Correct.
This is not the case for ground based, but it's also true that when the data is good, it's so much better than what you can get from space. So indeed, a lot of advances in science are done with those few selected, very, very good data sets that are used in a variety of ways. And I think that your example on Wednesday with one data set that we use for putting nature papers, right, or something like that. So that is something to keep in mind, because, again, everybody gets always scared.
And also keep in mind that you spend a lot of time co-aligning, cleaning, shifting. Some images will not be co-aligned, stretching, and then finding out that you made a mistake and you will have to start all over again. It takes a while to prepare data, and especially when you want to several instruments and co-align everything together with different field of view, different pixels, different everything. So that's a little bit different from Hinode and SDO data, but also exciting.